All right, let's put our Lewis dot structure drawing skills into practice. I want to do an example where we draw the Lewis dot structure of carbon disulfide. So the way we can do these sorts of problems is to go through the handy hints one at a time. Step 1, try to assign the central atom. It is often the unique atom, and it is typically the most electropositive atom. Here we have carbon being the unique atom and the most electropositive atom, so that outweighs sulfur being a third row atom. So we're going to assign carbon as the central atom here. Now, we want to count up the total number of valence electrons that are available. So in step 2, we have carbon bringing 1, 2, 3, 4 valence electrons to the table. And we can see that by going to the periodic table and counting across on carbon's row. It has 1, 2, 3, 4 valence electrons. That's how we get that number for the number of valence electrons in carbon disulfide. So carbon has 4 electrons. Each sulfur has 6 valence electrons, and I can see that by going to the periodic table and counting across to sulfur. 1, 2, 3, 4, 5, 6. Just counting across in its row, I can see that sulfur brings 6 valence electrons to the table. So sulfur has, 6 valence electrons. But we have to bear in mind that there are 2 sulfur atoms in the molecule. So I'm going to multiply that by 2, and that's going to give me 12 electrons total for sulfur. Now, the 4 plus the 12 means that I have 6 electrons available. 6 electrons that the carbon and the 2 sulfur, 16 rather. 4 plus 12 is 16. 16 electrons that the carbon and the sulfur bring to the table. Now we can move on to step 3, where we calculate the total number of electrons needed for each atom to possess its own noble gas shell. So carbon needs 8 because it obeys the octet rule. Sulfur also obeys the octet rule, needs 8 electrons times 2 because I have 2 sulfur atoms. So that's going to be 16. 8 times 2 is 16. And 16 plus 3 means that I have 24 electrons that are required total. So now I'm going to go to my handy hints, step 4, and subtract the number in step 2 from the number in step 3 to get the number of shared electrons that are present. So 24 electrons required minus 16 electrons available means that I'm going to have 8 electrons left that need to be shared. I need to divide that number by 2 to get the number of bonds. So 4 bonds. Now I need to take the molecule and start assembling the sigma framework. But before I do that, I can go to step 5 and subtract the number in step 4 from the number in step 2 to find the number of electrons that are in lone pairs. So let me do that. The number in step 4 is 8 electrons. So 16 electrons total that I have available minus 8 electrons that get shared means that I have 8 electrons that are going to be in non-bonding lone pairs. All right, so now I can go to step 6 and draw the sigma framework of this molecule. The sigma framework is just the single bonds. And I know I have CS2. So C, I said, is going to be the central atom. So I'm going to draw the S's around it. And I know that I have 4 bonds. So here I'm going to draw the sigma framework, which is just the 2 single bonds. Now I have to go on to step 7. And if bonding electrons remain, I'm going to assign them by making some of the bonds multiple. So I had 4 bonds, and in my molecule, so far I've only used 2 bonds. So I'm just going to double them up so that I have all 4 bonds. Now, I guess another possibility that I could have drawn would be to arrange them asymmetrically so that I have a triple bond on one side and a single bond on the other. So those would be the 2 possible arrangements that I could do for this is now step 7. So this is step 6 and step 7. Now I want to go on to step 8 and assign the lone pair electrons from step 5 to complete the octets. So I know I have 8 electrons in lone pairs, and I want to draw them in a way that everybody's going to have an octet. Now, carbon is done. It has 2, 4, 6, 8 electrons associated with it, so it doesn't need any lone pairs. However, each sulfur needs 4 electrons around it to complete its octet. So I'm going to put the extra electrons around the sulfurs in that molecule. Now, in this version, this sulfur already has 6 electrons that it's sharing, so I only need to put 2 more to fill its octet. However, for this guy, I need to put electrons around all the sides of it. Okay, now I want to determine the formal charge on each atom. To do this, you subtract the number of electrons currently associated with the atom, those in lone pairs, plus 1/2 the number of electrons in bonding pairs, from the number of valence electrons possessed by the free atom. And the formal charge must add up to the total charge on the molecule. So this sounds difficult, and it is kind of a pain at first, but you will get used to it, I promise. You want to just follow these directions very carefully. So for carbon, the formal charge is going to be here in this version of the molecule. The formal charge is 4 electrons possessed by 4 valence electrons possessed by free carbon. I'm just going to write it as a 4 to simplify things. Minus, now we count up half the bond. So 1, 2, 3, 4 gives me 4. So the formal charge on carbon is actually 0, which is the ideal formal charge that you want. For sulfur, the free sulfur atom has 6 valence electrons, right? And I'm going to subtract each lone pair electron counts for a full electron, 1, 2, 3, 4, plus half of each bond, 5, 6. So 6 minus 6 is 0. And this one would be the same. 6 minus 6 equals 0. You can check that definition carefully and make sure that you understand how I did that. Now, over on this molecule, carbon, once again, is going to have a formal charge of 0. But this sulfur is going to have a formal charge of what? 6 minus 1, 2, and then half of each bond, 3, 4, 5. 6 minus 5 equals 1. So this has a formal charge of plus 1. This sulfur is going to have a formal charge of 6 minus each lone pair electron, 1, 2, 3, 4, 5, 6, and then half the bond, 7, minus 1. So the formal charge here is minus 1. Now, you notice if I add the plus 1 and the minus 1, they add to 0. So that's the formal charge adding up to the neutral charge on this molecule. So in the next lecture, we'll talk about how to say which version is